Welcome to video 3, Magnetism Basics. In this video, we'll discuss the basics of magnetic fields and how they apply to inductors, solenoids, transformers, and relays. First, let's talk about magnets. Magnets create what is called flux lines, and those flux lines added together are what's called a magnetic field. And the thing with magnetic fields is they will always take the easiest path back to their opposing side. And if you have multiple magnets put together, they will work together to create the easiest path for those group of magnets. As you can see here on this set of magnets, they're opposing. And when they're opposing, they like to repel. They like to push themselves away. The the flow of this magnetic field likes to push those magnets away. While on the one right below, because they're opposite sides, they like to attract. This magnetic field is super strong the closer those magnets get. And what creates the strength in the magnetic field is determined by how many flux lines there are. Now, the same could be said as far as wiring goes. When you put current through a wire, it creates a magnetic field around that wire. If you just have a standard wire and you're holding it, as you see in this picture here, with this style of grip, this is called the right hand rule, and that determines which way the magnetic field is surrounding that wire. If you hold it with your thumb pointing to the negative side, the way your fingers curve around the wire, that's the direction that magnetic field is. Electric fields are circular, and with this wire, you can see a better representation here. Now, if your thumb is pointing this way, the way your fingers would curve around the wire would be in a circular motion like that. And if your thumb was pointing towards you, right hand rule, it would curve the opposite way. Now, if you run multiple wires together, those magnetic fields will cause those wires to repel and attract the same way those magnets work. So if you have two wires running in parallel, kind of like this, if the voltage is both positive, positive, negative, negative. If the voltage, if you have these two wires running in parallel, they'll create magnetic fields. So let's again think of our right hand rule. We have our thumb that points this way. We have our fingers that curve around like this. So that means the magnetic field is going to curve around like this. Curve around like that. But in the other wire, it would be exactly the same. And they would attract because when it comes back around, you have the arrow pointing up and this arrow pointing down, and those magnetic lines of force, those flux lines, they cancel out. If you have opposing flux lines, they'll cancel out, so there'll be less energy surrounding the inside here between the two wires, and they'll attract. Those wires will attract together. Now, if you have the opposite, so you have negative, positive, and then positive and negative, two wires running along this way, and then you had the same thing, same magnetic field idea. One line would go this way. Think of it now. Our thumb's pointing the opposite way, and our fingers are curving around like this. This is a bad hand. Sorry for that. So that magnetic field would then curve around the opposite way. So we would have that magnetic field face this way. I'm going to draw that a little bit different. Face this way. Now, if we're looking at it from down the barrel, let's say we have the positive side here. Our wire comes along here. This is our negative side. And our magnetic field lines of force curve around like this. And on this side, our magnetic lines of force will curve around like this. And they're flowing in the same direction. If they flow in the same direction, they add together, they create a stronger line of force in the center. And that stronger line of force will push those wires away. Now, we have things here. This is basically called an inductor. An inductor is basically creating a stronger magnetic field by looping a wire into this loopy shape. Those magnetic lines of force, they add together. Like if you think about it the way when we're talking about this, we're talking about those wires being side by side like that and they'll add together. When we loop it around like this the way it's flowing, they're flowing in opposite directions, and when they flow in opposite directions, they combine lines of force. When they combine lines of force, they create a whole lot stronger of a magnetic field around this inductor. Now, an interesting thing to note, I drew in this picture here, it's an iron core in the center of this inductor. Magnetic lines of force try to take the shortest or easiest path. And there's nothing easier than having some sort of ferrule material in the center that can concentrate those lines of force. So what this is just created an electromagnet. This is a really strong electromagnet. These are the types of things that are used to lift scrap cars in scrap yards. They can be very, very strong. And all that's being done to control it is based off of how much amperage you're putting through. Now, one thing to note, how many loops there are will determine how strong a magnetic field is. The more loops you put on, the stronger the magnetic field is going to be. This is important when we're talking later on about transformers. And this is also important when we're talking about what the output's going to be as far as the magnetic field strength. The magnetic field that's created is directly proportional to the amount of loops and the current applied to it. So if I have a current of 10 amps and a loop of 10, the magnetic field is going to be equivalent to if I had 1 amp with 100 loops. They're going to be the same magnetic field created if I had 10 amps but 10 loops and 1 amp with 100 loops. The magnetic field that's created is the same. Now, one thing to note, when you have inductors, you have a rise and fall of magnetic fields. And when you first put voltage to an inductor, it takes time to build up that magnetic field. So that magnetic field doesn't end up like this off the hop. It has to build up to that magnetic field. If you were to look at it on a graph, you would see something that looks kind of like this. And the reason why it does this is because you have multiple sources of power that are opposing each other. That buildup of a magnetic field can induce voltage the same way that putting voltage on can create a magnetic field. They go hand in hand. So if you had that magnetic field created, let's just discuss here real quick. If I hooked up a multimeter in voltage DC to a piece of wire and I had a magnet and I move this wire through the magnet, you're moving it through the magnetic lines of force of this magnet. As you're doing that, voltage gets induced in the wire. If you move it up and down, they're going along the lines of magnetic force, nothing happens. If you move it through the lines of magnetic force, that's how you induce current. So if you were to take that wire and you were to move it really fast forward through this magnetic field, you would actually induce a current through that wire. That being said, now when we talk about amps over time, as we're building that magnetic field up, as this inductor is building its magnetic field up, those magnetic flux lines are going through these inductor coils really, really fast, which is inducing a back current, which we call counter electromotive force. And basically, that is When we have multiple ways of creating power and they oppose each other, it will reduce the amount of power that's actually being put to it. So your amperage is super low at the very beginning because as it's putting that current through, it's building those lines of force. Those lines of force are inducing a current that's going the opposite direction into the direction of you supplying that current. And that push backwards is what causes the amperage to be so low at the beginning. And as you're building that magnetic field up and those lines stabilize, now that this line is stabilized or these lines are stabilized, they're not going to put any back current because now they're not pushing those magnetic field lines through the inductor. Now they're stabilized, now they're consistent, and they're staying where they want to be. Now there's no more back current, there's no more counter electromotive force. Therefore, your inductor is not going to impose that current anymore. Now, I also want to note this is a diode and this is a resistor. These are important because when you all of a sudden take the voltage off, you cut voltage here, you cut voltage here. Keep in mind exactly what we talked about that counter electromotive force. Keep in mind what we talked about as far as it wanting to create that back current. Now, as those lines collapse, it wants to induce current the opposite direction in which it originally was. So when we build that current, it wants to put that force backwards. But when we collapse that current, it wants to put that force forwards. So it's going to induce a huge amount of current in the forward direction. Now, you might have a 12-volt battery. The amount of current and voltage you can supply by collapsing a magnetic field is way higher than that 12 volts. So they have things like resistors and diodes so that when that magnetic field collapses, it induces a current and it can create that current and it can flow through that resistor, slow it down, and so therefore it doesn't do damage. Or you can have that diode where it induces a current, it goes backwards, and it keeps flowing through until it can actually dissipate that energy. Now let's talk about transformers. Remember how we talked about the amount of loops changing the magnetic field strength and the magnetic field strength itself determining how strong or how much current you can put through when you have a collapsing magnetic field? When you have AC voltage, you always have a buildup and collapse of magnetic field because you think of how AC current works like this. As it's switching directions on voltage, it's now collapsing magnetic fields. It's putting voltage the opposite way. So every single time it switches direction, it's causing a collapse on a magnetic field. So now you have a transformer, and let's say you have 10 windings here and 100 windings here. You are multiplying your voltage by 10 times. So let's say you had 12 volts here, you would have 120 volts here. This is called a step-up transformer. If you were to do the opposite, and you say you had 100 windings here and 10 windings there, you would have a reduction of 10. So when I was talking in my very, very first video about how we used high voltage so we could limit the power loss through power lines, we use things called step-down transformers because, as I said, the longer the line, the more the resistance. So they supply a higher voltage so that they don't lose as much in the longer process. They limit the current, but increase the voltage. Now, when they bring it to your house, they have these step-down transformers. Instead of having tens of thousands of volts or hundreds of thousands of volts, they limit down to your house being 120 volts using step-down transformers. Okay, I didn't finish all the topics I wanted to cover, but I'll cover them in a part 2 of this video. So look out for that video, and I'll cover capacitors, relays, and solenoids. Thank you for watching.